Now I'm delighted to introduce our speaker, Florian Wiesner. Florian is a researcher specializing in the integration of machine learning and physical sciences. He holds a bachelor's and master's degree in chemical engineering and completed his PhD at RWTH Aachen University, where his research centered on fluid dynamics and machine learning applications, topics near and dear to my heart. During his doctoral work, he contributed to a diverse range of projects spanning metal 3D printing, electrochemistry, and cartilage repair using robotic in-wound printing systems. His current research focuses on AI for science, particularly on developing machine learning models that can capture and generalize fundamental physical laws. This work aims to accelerate scientific discovery by creating tools that understand the underlying physics governing natural and engineered systems, moving toward foundation models that can be applied across multiple scientific domains. Today, Florian will be giving a talk titled Towards a Physics Foundation Model. So please join me in giving a warm welcome to Florian. All right, over to you, Florian.
Awesome. Yeah, thank you for the kind introduction. So the title of my talk was Towards a Physics Foundation Model, but I realized that maybe before I'm coming to the title and the actual work that I've done and what I want to talk about, we need some definitions, and that's why I'm starting with these physics surrogate models here, because the physics models I want to talk about are these surrogates models. So these are models that are replacing numerical simulations and give you something like this, what you see in the image here. So for example, if you want to know how air moves around a car, you are an engineer and you want to optimize the shape of the car, for example, then you would run very, very costly simulations. Could be weeks or even months, depending on the simulation, to get this outcome of like the velocity, for example, and the density of the air moving around. There's been an ongoing process over a few years already of like replacing these numerical solvers with machine learning models, just speeding up the whole process, making prototyping much more efficient and fast. Okay, so let me see if the animation works. Yeah, so the current state of the art for these physics surrogate models is usually that these models learn one physical system. You have a car in this example at a specific time step, and then the model just predicts the next time step. So what happens, for example, in this case with the air around the car, what happens in the next time step. And then you do this for 100 or thousands of time steps, and then you have your simulation basically. And this works relatively well. I think it's not ready for like commercial applications yet, but it's still well established and produces good results. There are many of those, and I thought I might mention those just so that you have heard the names, which are the most common ones. So there are the operator networks. These are machine learning models that learn a operator in the mathematical sense. So these models transform a function to a function. This is different to, let's say, normal neural networks, which transform a specific state to another state. So the advantage of these operator networks is that they are, for example, discretization invariant. So you can zoom in your simulation or zoom out. You can choose different points you want to observe, and these models can do everything like this. So these are quite interesting in itself. This is just other dimension. Then maybe you have already heard of the neural ODEs, which is another example of taking a neural network as a differentiator and then using a numerical integrator, basically combining a numerical solver with a hybrid model. And there you can also, of course, use different architectures, MLPs, UNets, transformers, whatever. And maybe the most prominent one of these physics surrogate models is the physics-informed neural network, PIN, which is basically a normal neural network. It just learns, has an additional loss function, which is physics-based. So you compute some physical quantities of the system, and therefore the model learns faster. And as I said, these models are all well established. They work nice on some problems. The problem is they don't do well in generalization tasks. So just as our example with the car, now we are designing a completely different car, a racing car for Formula One, for example. And now the car is moving much, much faster. And therefore, for example, we have to consider the compressibility of the air, which we maybe wouldn't have to do in the previous case. And now the model, suddenly the physical system is basically a different kind of partial differential equations. You have to take into account other things. You maybe have other boundary conditions, and so on and so forth. And in these cases, the current state-of-the-art pins and neural operators, they don't work well. And usually you just have to retrain with new data sets. And of course, this is what we don't want to do. We don't want to retrain for every new problem. We need data for this. We need time. We need compute. This is basically impractical for like engineers to just quickly test out designs and different stuff. So when we now think about a foundation model, this is just a definition of like a nice definition of a foundation model from one of the papers calling for these kinds of foundation models. Foundation models are basically models that have this generalization capability. So you don't have to retrain, or you only need to fine tune a little bit with very few data points. And yeah, this is basically what we want to have in this physics model, physics surrogates space. Okay, so the first true foundation model we had, or maybe the most prominent one, is the LLM, of course. You all know this. This is very, very good at generalizing. It can do a bunch of different tasks to a very high accuracy, sometimes not as high as we want, but still pretty good. So yeah, it's truly impressive that they can do coding and summaries in one go, right? One model can do both, for example. And the question now is, can we do something similar for physics? And that would be like a physics foundation model where we have chemistry, mechanics, quantum mechanics, astrophysics, fluid mechanics, everything in one case. So this would be the best case, non plus ultra example, very far in the future, probably, till we get to this point. But yeah, this would be the best we could wish for. Yeah, and these physics foundation models basically are then predicting the temporal evolution of different physical systems. So again, you want to see how air moves or quantum states change or molecules behave. And this model would then be capable of predicting all of those stuff depending on what you ask for. And this basically brings me to the actual title slide of my presentation towards a physics foundation model, because yeah, we tried to take a step in that direction of such a physics foundation model. And you can see here some of these different physical systems we looked at. And yeah, I will get to that later. Okay, so currently there are already some physics foundation models or something similar, multi-physics models out there. Like in the last 2 years, there were some publications in that space, and they usually focus on fluid mechanics, and that's what I'm going to focus as well, because it's just the space where we have the most data and it's the easiest to handle. We would hope to combine this with new kinds of physics, but yeah, fluid mechanics is just much easier to generate data. You can use image or like 3D images just to describe the data. So it's easier than chemistry or quantum mechanics maybe. That's why most of the papers and also our paper are focusing on this one. Yeah, and as I said, there are a bunch of different architectures, all doing complicated, interesting stuff. Basically, all doing the same, taking a bunch of data from different physical systems, training them in one go, and then have a model that can predict multiple of those systems to a sufficient quality or sufficient accuracy. The issue we currently all face with this physics foundation models is, so what we want to do, we have a time step 0 or time step I. This is, for example, a velocity field, right? So how the fluid moves in which direction, for example. And we want to predict the next time step. The problem is we have, if we just get this T0, it's very hard for us to know what's happening in this system. And I can visualize this, or maybe as an example in this case here. So if we look, for example, at this spherical ball here, or this dot, and I'm going to tell you it's moving, yeah, and I can maybe even give you the vectors of movement, so in which direction the ball is moving next. You still don't know, for example, what the boundary here is. Is this like a wall and the ball will be bouncing off it, or will it just go through and this is just an artificial boundary? You don't know. You also don't know if the ball is rigid or soft. So from the single image or this single snapshot, it's extremely difficult, or sometimes even impossible, to differentiate different systems. You don't know what system you're looking at. And this is one of the fundamental questions or problems that these multi-physics models have. If you have only a single physics model for a single physical system, that gets much easier, of course, because you can just memorize, this is the system I'm looking at. And that's why the common solution for all of these models I just talked about is basically fine-tuning on a single data set. So you pre-train with multiple data sets, maybe give it a class label per data set, so the model knows what it's looking at. And then you fine-tune on a single data set, and now the domain is clear again, right? The model knows what it has to do. This is a, I don't know, fluid dynamics system with fixed boundaries, and it's incompressible, and there's no temperature change. And then, as I said, the model knows what it's looking at, and then it can predict pretty well. The issue here is, what we actually want is a foundation model without retraining, right? This fine-tuning is something we don't want. It's still better than the full retraining, of course. And there are lots of cases where fine-tuning makes total sense. But if we could, we would definitely just avoid the retraining and have a language model, right? You don't have to fine-tune again on translation or fine-tune again on coding. You have a general purpose model which can do many things reasonably well. So our question was basically, can we get a model without any retraining still capable of doing multiple physics, or generalized to many physics? And yeah, as I already hinted at, we can look at language models. How are they doing it? In language models, you just give it a PDF. And if you just give it the PDF, for example, the model doesn't know what to do with it. What you do is usually, you just give it a prompt, right? You tell it what it's going to do. And this is basically the context of the model. And you change the context, and therefore the model does a different task. And this is called in-context learning. LLMs are incredibly good at this. It can basically, each of your prompts is basically new tasks that the model has never seen before in this detail, but still performs well. So the question we had, or the idea that we had, is, can we create a physics model and give it context about our system? And therefore, it does not have to get fine-tuned. It just knows from the context what's going to happen next. So what we need is a time series. So if we look at a video of this system, we clearly can see what are the boundary conditions. We can see whether the balls are sticky or if they're just bouncing off each other. We can see if there's gravity or not, right? All of these things can be learned from the context. So the idea is basically, we give the model a context, a snapshot or multiple snapshots of physics data of preceding physics data, and then predict the next step. Yeah, so this is basically the grand idea. It's pretty simple. And also, for fairness, I have to mention multiple other multi-physics models or foundation models already used this kind of multi-step prompt, but they never viewed it as a tool to do this in-context learning for completely new physics without retraining. They always did the retraining as well and just used the multiple steps to make more accurate predictions. And our basically very simple but still hard idea or question is, can we get this to work without any retraining? Okay, so we still predict the next time step. So this is an autoregressive model. We get, in this case, 4 time steps, predict the 5th one, or the number here is wrong. T3 should be and T4. I'm not counting correctly. So basically, you get a bunch of time steps and predict the next one. You can choose 2 or 4 or 8, depending on how accurate you want to be and how much time steps you already have. Importantly, if you choose just 1 time step, the whole model doesn't work. And we also showed that you need multiple of these time steps to do this. And then, of course, you do it for the next step as well. So you can then append the time steps you already generated, so the T5 in this case, to your preceding context, and then we predict the next one. So this is basically very similar to the next word prediction in LLMs. Next word, next word, next word, next word. So this is the physics in context learning idea. And of course, in physical simulations, you need many more of these physical states. I just talked about the velocity first, but for many of these fluid dynamics cases, you would need something like temperature, pressure, density, and maybe even some other fields. And now if you think about including something like magnetism or light or chemistry, of course, you would need even more of these physical states or physical fields. But in general, the model works very similar, whether you're just using one of these or multiple of these. Just for each of these fields, you predict the next time step and then do the same over and over again. Okay, so just a little bit of methodology for our approach. Again, as I said before, we also looked at fluid mechanics because that's where we have the most data, and I generated a bunch of data. So quite a lot actually. And had just for the fluid mechanic guys in this meeting, I used incompressible flow, compressible flow. I introduced some heat to some of the problems and also used capillary flow. So this is flow in very tiny pores, for example, micrometer sized pores, where the fluid behaves much more different than in large pipes, for example, or around airplanes. And the important thing is, even for just the incompressible flow, I created multiple data sets where a single time step is not good enough to differentiate the 2 time steps. So for example, you can just change one of the boundaries to a periodic boundary instead of the wall. And from a single time steps, you might not be able to differentiate it, even if you look very, very closely. While while 2 or 3 time steps are already enough to immediately see what's happening. So this was a requirement for this kind of data. So this is basically our data set. And then, as I said, very simple model. We take our state, we put it into our magic machine, and then we predict the next time step for all of these fields. And because, this is a machine learning presentation, I'm going into a little bit more detail here, but not too much. So we're actually using a spatial transformer. So this is just a very, very basic transformer, normal attention, normalization layers, whatever. The only thing different is it's attending to like in time and in space. So it looks backwards and forwards. It's basically a video transformer, so nothing too fancy. And also the tokenizer and detokenizer are not completely wild or something novel. So just to say that, or just to explain that a little bit more in detail, we're using these tubelet embeddings. So we basically cut out little cubes of our data in space and in time, and this is compressed into one vector, and then the vector is our token, and with this token we're doing this normal attention. So this is also something already introduced into video transformer and nothing new. And then maybe one of the more interesting changes we did is basically we used this idea of neural ODEs so our machine learning model now, this transformer here, is now predicting only the spatial derivative, the temporal derivative of our system, and not the actual state anymore. And then we can use a numerical integrator to integrate to the next time step. This was actually one of the more important changes or discoveries, that this makes a big difference here. Yeah, so nice little detail, but also nothing really fancy. And that's why I also did this slide. So this architecture is not like super crazy and magical, and this was on purpose. I showed you these other models before, and they work great, and they have some really, really nice ideas, which might be actually better than our model in some cases. For our first approach here, we wanted basically to adhere to this bitter lesson approach. Don't make it too complicated. Try to scale up first. Try to look how a normal model would work, and just generate more data if you need more accuracy, or train for longer. Pour in more compute instead of doing all this crazy engineering and fine-tuning of the model. So yeah, just a heads up, basically, you won't find any like super new idea here in the paper about a new model architecture, which is basically a feature and not a bug. Yeah, and with this, basically, we can go to some examples of like how this should look. So these are basically results. We can have a ground truth of our simulation. So this is now a fluid flow, a velocity field, how liquid moves around. And now we have the ground truth and the prediction. And yeah, I can now talk a lot about how good these predictions are, or how bad they are, where they fail. But in general, yeah, you can see they are quite good for these more simple problems. Yeah, we have different kinds of simulations or predictions. As I said, this is, for example, now with some rigid obstacles in the fluid movement or in the fluid direction. We have some more sharp gradients, and on the right side, for example, this two-phase flow, this porous media flow, where like one of the liquids is displacing the other one. So this is now a completely different kind of physics, where, for example, surface tension is really important, and the model is still doing reasonably well. And then very complex systems with heat involved, with sharp gradients involved, where the model is still doing good or doing well. Okay, so yeah, these are just nice videos I'd like to include, just to do some picture or video science. Always nicer to look at this compared to some figure or like plots or charts. Yeah, so this looks all great. The problem we still have is these are all training data sets, right? So this is the test split, of course, of the training data, but it's still systems that the model has seen before, right? Similar systems, similar boundary conditions, similar fluid flow. So what we wanted to do, just as a reminder, is we want to check if the model is also applicable to completely new physical systems. And that's why we, for example, changed boundary conditions and it's also evaluated on different boundary conditions where the model is also performing nicely. And then completely new physics. So for example, this shock wave here against the cylinder with like supersonic flow. Or on the right side, this is something happening in astrophysics between a hot and a cold gas. This is something that the model has never seen before, nothing even close to this. So these were basically our hardest tests on how the model can work with systems that are completely different. And you can see it is nice. It works well, better than we expected. But of course, we still have big issues here, right? I mean, this looks like qualitatively looks nice, but you can see of these patches here, these artifacts on the left side. So this is not something you can use to work like on a car or like do some engineering and base your budget decisions onto this, right? So this is basically the hardest problem you can get to for these models. Completely new physics, never seen before, not trained on, no fine tuning on this, and still ask the model or task the model to predict the temporal evolution of the system. And yeah, it works well. We were surprised, and this is basically a nice first step. That's why it's called towards a physics foundation model, but we are still not there yet. And this is what I wanted to say with this slide, just to make this completely clear. There's a reason why I didn't call it the first foundation model for physics, but like this nice towards, which is always nice in scientific publications. Yeah, so this model is not useful yet. I'd argue no physics-informed model is currently really useful for engineering tasks with real money behind it. But it's a nice direction and maybe a first push towards these kinds of models that have this train once, deploy anywhere paradigm, where we do not have to do this tedious retraining, generating data, evaluating again, but it just works right off the box. And one example, for example, why it does not work really well. Now you can look at some very long horizon rollouts, and now you can immediately see how the simulation quality degrades. So this is especially apparent in the middle section here. On the bottom is the prediction, and the prediction looks nice. And on the first view, you would immediately say, oh, this is a nice prediction. It looks very physical, very realistic. But if you actually compare it to the top simulation, you can actually see that the swirls are in completely different places, for example. So yeah, basically this is my word of caution here at the end of this presentation. These models are very interesting and I think exciting possibilities, and we should definitely work on them in the next years, and I'm planning to do so. But we are definitely not there yet to really say, yeah, we can just use it in any task where we actually care about the results yet. Yeah, and basically with this, I'm a little bit early, but I want to come to the conclusion here that these physics foundation models, and not just mine, but basically all of the other ones as well, they're usually focused on fluid mechanics in the most cases. And that's one area of research where I think we should look into, like, how can we combine multiple of those physical systems together to create an actual foundation model. They can already, inside this one domain of fluid mechanics, do multiple systems, especially when you do fine tuning, but even without it, you can get some form of generalization. But as I said, the accuracy of all of these models is still lacking, and yeah, we need some more. Yeah, and basically just the slide, so you've seen the faces of my supervisors as well. Just so you've seen them once. Yeah, maybe some QR codes are also interesting for you. And after that, because I don't like to end with this boring slide here, also maybe an outlook. So as I said before, we want to combine multiple of these physical domains together, not just fluid mechanics, which might be a task that takes multiple years or even decades to achieve, but I think it's very, very interesting when we do so. And something maybe more in line with what you guys also at First Principles is doing, the theoretical physicists or theoretical scientists, which is more thinking in reasoning and language and equations. And I think one of the interesting parts I want to tackle in the future is combining these two. So just very broadly, something like a vision language model, right? Where the vision is not a natural image, but the vision is a simulation. And now the agent or the model or the reasoning LLM can now think about this simulation, knows about the boundary conditions, and can do much more accurate predictions or find out new stuff about this thing. So this is maybe the ultimate goal and very, very interesting approach. Although I'm not sure how feasible this is, at least not in the next couple of years, maybe, but still interesting. Yeah, and with this, I'm already finished and hope you have some interesting questions for me. Thank you.